And our next speaker is Elizabeth Gall. She is a researcher at the Max Planck Institute for Infection Biology and will be speaking on age at vaccination for measles. Take it away.
Thank you. Thank you for the opportunity to speak as well. So as Kurt said, I'm looking at estimating the optimal age for measles vaccination. And this, oh, come on. There we go. So this is based off this relationship between the vaccination age and vaccine effectiveness. So this is data taken from a systematic review of measles vaccine effectiveness with different vaccination age. As you can see, we starting from around 6 months.
We're still seeing you on slide 1. Are you still on the title slide, or have you?
I moved on. Okay. Oh, resume sharing. One sec. Okay, I'll stop sharing and start again. Sorry, guys.
No worries. This is kind of baked into the hybrid experience.
Okay.
Now we're seeing measles increases with age.
Perfect. And then if I move on, you can see the change?
Yes, indeed. Thank you.
Excellent. Okay, take 2. So as I was saying, measles vaccine effectiveness increases with age. So this is from a systematic review. As you can see, from around 6 months up until about 18 months, we get this increase in vaccine effectiveness. And there's a couple of reasons why this is happening. The first of which is from measles maternal antibodies blunting the immune response. And then the second is from the immaturity of the infant immune response. But regardless of why it happens, this is going to lead to a trade-off in risks when we start choosing the vaccination age. So this red curve here is just the inverse of that curve you just saw. And what we see is that as we increase the vaccination age, this risk of vaccine failure, so an infant being vaccinated and then going on to get measles later in life, is reduced. But this goes hand in hand with another risk, so the risk of being infected prior to vaccination. And the longer we wait to vaccinate, the more time that infant has to go and interact with people who have measles and thus catch the infection. And we can combine these two, and this will give us the overall risk of measles infection. And what our method for estimating the optimal age of measles vaccination is based off the idea that there's going to be a minimum age to which minimizes this risk of which we should vaccinate. So some of you might be flashing back and going, I'm sure I've seen this last year, because I did present it last year. But the project has kind of progressed it quite a lot, so I still think it's important to present. So what I previously presented was a method for calculating the optimal age, and a few synthetic applications of this method to synthetic populations. And we've expanded those applications, but we've also tried to expand to better represent low and lower middle income countries. So to jump back to this plot, so we've got this risk of measles infection. And what we want to do to try and work out the optimal age is to quantify this risk. So the way we did this was using a mathematical model. And this isn't the full model, but it's kind of similar to what Scott just presented. And the important thing is that it's age structured. And because we want to model vaccination at different ages, we actually have quite a fine age structure. So we model age groups monthly from birth up until 60 months, so 5 years. And we took that model and then used it to estimate the equilibrium annual measles incidence, identifying the optimal age to recommend measles vaccination as the age corresponding to the minimum incidence. So now we had a method, and we wanted to test that method, but we also wanted to see what factors might affect the optimal age. So we tested kind of 3 different things that I'll present here. So the first was the social contact matrices. For those who haven't encountered them before, social contact matrices is matrices which quantify how much contact one age group will have with another age group. So I've got 2 examples here, which are very cartoony examples, really, but trying to show what these contact matrices look like. So you can see for South Africa, the children and children tend to interact a lot, and this is sort of the largest contact in this population, with adults and adults contacting each other less, and then children and adults and children having even less contact with each other. Whereas in China, you see that the majority of the contacts are happening between adults and adults. And this is kind of part of the one child, relic of the one child policy. The second thing we considered was the vaccination coverage, the first dose vaccination coverage. So we varied this between 45% and 85% based on the WHO reports of vaccination coverages in countries with greater than one case per year per 100,000. And then the third thing we varied was the transmission level. We described this transmission level as low, medium, and high, but this doesn't really mean anything, right? So to translate this into something meaningful, what we looked for was mean age of infection in the pre-vaccine era. So this is data taken from Anderson and May, which is reports of the mean age of infection before vaccination was introduced or widespread. And there are about 6 or 7 reports which varied by location. But these reports, reported age, tended to kind of group naturally into three different ages, which we have described as low, medium, high based on that. So when I describe something as a high transmission level, this is what I mean. I mean that the mean age of infection is between 24 and 36 months. And to translate that into the model, we for each social contact matrix, we parameterize the model with that social contact matrix. And then we varied the R0 to try and achieve these mean age of infection, this target mean age of infection. So initially we did some variation. We tried to do this just by varying the R0 between 10 and 20, based off previous reports of the R0. But we found that this wasn't really flexible enough to achieve the full range of these mean age of infection that we saw in these historic reports. So we had to introduce another parameter to increase the flexibility, which was the transmissibility of under 5-year-olds relative to the rest of the population. And so we fitted the model to the target mean age of infection based on that. And we found we were able to reproduce this full range of the mean age of infection. And so thanks to that, we've got a model, we've parameterized that for the different transmission levels and also for the different social contact matrices and vaccine coverages as well. And now we have some results for that. So this plot is something you're going to see a lot. So I'm just going to take a second to sort of go through it. So along the x-axis, we have the different possible optimal vaccination ages. So the vaccination ages that we tried varying from 6 to 20 months. And the coloured boxes are where the optimal vaccination age occurred for one of the scenarios we tested, with the intensity indicating how the proportion of the scenarios tested which occurred at that optimal vaccination age. So this is specifically an example for the USA social contact matrix at 45% vaccine coverage. But what you can see here is that as we increase the transmission level, the optimal vaccination age is going to decrease. And this does make sense when you start to think of it in terms of this schematic here on the right. We see that the pre-vaccine infection probability, when we think about that transmission level increasing, we can see that this yellow curve will increase in steepness. So this crossing with the vaccine failure curve will be at a younger age. So vaccinating the optimal, minimizing the risk will occur at a younger age. Secondly, just for context, I've indicated here when the WHO recommended vaccination. So at 9 months for low transmission settings and then for 12 months for high transmission settings. And then the next thing we looked at was the vaccine coverage. So this is, for example, an example in Moscow at a low transmission setting. And what we see for the vaccine coverage is that more vaccine coverage leads to increased optimal age, which again kind of makes sense, right? You can think of it either in terms of the transmission level, where increased vaccine coverage will reduce the transmission level, so leading to an increase of optimal age, or in terms of this schematic again, where increased coverage will lead to reduced risk of measles infection. So this crossing point and this minima will move to old vaccination ages. Then the final thing we looked at was the social contact matrices. So we tested 7 social contact matrices, but I'm just going to show you 3 here. So these are the most extreme examples. So South Africa and China, and then Japan in the middle, just to show some more context. And you can see that there's a large difference between South Africa and China, even when we're keeping the transmission level and the vaccine coverage the same. So medium transmission level, 45% vaccine coverage. And this really is driven by the amount of contact we have in the younger population, with South Africa having very high contacts in the young population, whereas China has really very low contacts in the younger population. And also to try and better understand what's going on with these social contact matrices, we tried clustering the contact matrices based on the optimal ages across all scenarios, so all transmission levels and all vaccine coverages. And we found that for all but 2 of the scenarios, so 13 out of 15 scenarios, we needed more than 3 or more, we needed 3 or more clusters to fully capture the variation in optimal ages, perhaps suggesting that more recommended ages are needed than the 2 recommended by the WHO. And then finally, to kind of wrap up this first part, here are the overall results from all of these social contact, all of our scenarios that we tested. What's important to note here is that there's a lot of variation in these optimal ages. So it goes all the way from 6 months in South Africa up to 20 months in China as an optimal age. So briefly to summarize, we found that the optimal age varies between population, and this optimal age is going to depend on the transmission level, vaccine coverage, and social contact matrices. But as I mentioned earlier, this wasn't perhaps a better representation of lower income countries, which is where the majority of measles burden is. So there were kind of a couple of reasons for this. The first was from the social contact matrices. Of the ones I spoke about earlier, the only one which came from a low or lower middle income country was India. So we chose to use social contact matrices from this paper detailed below from Mystery Hotel. And we chose to use those ones because they report contact rates on a yearly age group. So they report contact rates between year age groups. And as we are modeling a monthly age group level, we really want that resolution to be as high as possible. But the available matrices from this paper really don't cover much of these lower income countries. So there's only South Africa and Africa, and none of South America was covered. The second thing we didn't really account for was the demographic structure. So we had initially assumed a type 1 demography, where everyone survives until the life expectancy. Everyone survives until the life expectancy, and then everyone dies. And this is sort of realistic for some higher income countries, but not particularly realistic for lower income countries, for all lower income countries. So to better represent these regions, we extended our analysis. So we tried calculating the optimal age for social contact matrices from sub-Saharan Africa. And we used contact matrices from Prem-et-al, which had the advantage that it's better coverage of lower income countries, but it only reported contacts at 5-yearly rates. And then the second thing we did was we incorporated a different demographic type, so type 3 demography, which is characterized by high mortality in younger age groups, which and is more typical of countries in lower income, from lower income countries. So we took those. We tried calculating the optimal age for all combinations of demography, social contact matrices, vaccine coverages, and we kept the transmission level at a high transmission level. And we found similarities to our previous results. So here we see that the vaccine coverage is going, increases in vaccine coverage lead to increases in the optimal age. But we also see that these increases in optimal age are reduced for this lower income country simulations. And when we look at that on the whole, across all simulations, we find that a 10 percentage point increase in the vaccine coverage on average led to a 0.6 month increase in the optimal age in these high income countries, social contact matrices. Whereas in these low income country social contact matrices, there was just a 0.3 month increase in the optimal age. Moving on to the social contact matrices, we actually found no difference between the social contact matrices. And to sort of dig down into why that was the case, we looked at the actual social contact matrices themselves, and we found that they were incredibly similar. So this is the Mantle test statistic. For context, the closer it is to 1, the more similar the matrices are to each other. You can see that these 4 contact matrices from sub-Saharan Africa, from Prematal, are incredibly similar to each other. They're actually all above 0.99. So that explains why there were these optimal ages were incredibly similar. But whether or not these similarities in these contact matrices are due to them actually having similar contact structure in real life is kind of a question that I don't know the answer to, or whether or not it's due to these 5 yearly age groupings, which are hiding some of that variation. And then the last thing we looked at was the demographic types. And what we actually found was there was no difference between demographic types. At this point, I was questioning whether or not all of my simulations were wrong. But we looked again at the differences in incidence, and we did find that there were differences in incidence between the demographic type. And when we dug down into why these differences were happening, what it turned out was that the differences were due to the size of the age groups, which is kind of to be expected. We parameterize our model as having density-dependent transmission, and maybe we would have different results for frequency-dependent transmission. And then just finally, to give you an overview, this is all of the results for the lower income country simulations. And we see there's really not very much variation between these results at all, as compared to the higher income simulations. So to summarize, the optimal age varies less between populations in the lower income simulations. The impact of vaccine coverage was reduced, and both the demographic type and social contact matrices showed no difference in the optimal age. Although the differences in social contact matrices could be attributed to the similarities in actual contact matrices, whether or not these similarities are artificial is still a question that I and then just sort of round off. This study was kind of intended as a proof of concept, and so for application to the real world, we need some changes. For example, the endpoint we used was equilibrium annual measles incidence when calculating the optimal age. In reality, it may be beneficial to change that to a different endpoint, for example, measles hospitalizations in a given time period or deaths. Also, application to a real world, to the real world would require some level of model fitting of this model to time series of measles data. And then finally, we have applied this just to measles containing vaccines. But because of the reasons why the relationship between vaccination age and vaccine effectiveness occur, we would expect this relationship to be the same for other vaccines. And there is evidence from antibody titers that this is the case. So we would also expect that the method could be expanded to other vaccines potentially. in the future. So briefly to summarize again, we found that the vaccination age can impact measles incidence, and that the optimal vaccination age is context dependent and depends on the transmission level, the vaccine coverage, and the social contact matrices. But that this variation was reduced in lower income country examples, although better, higher quality social contact matrices would be required in lower income countries to better assess this. And thank you for listening. I hope you're still listening. It feels a bit like I'm talking to a black screen. Thank you to my lab, and here's a preprint if you're interested.
Thank you very much, Elizabeth. We are all here. It was an excellent presentation. We have time for a question or two. If anyone in the audience has a response to that, it is very good. I hope you can see, we probably actually can't see the audience, but we have a nearly full house today.
There is a question in the chat, if you would like me to read it.
Would you please? Thank you.
Yes, of course. Okay, so Han Fu, if I pronounced that wrong, apologies, has posted, "Thank you, Elizabeth, for the nice talk. Could you give a bit more detail about the yearly social contract matrices? Are they based on empirical data and/or contact diary? How does the contact pattern look in the under 5 group?"
Yes, of course. No, it's a super good question. So the contact matrices are developed in different ways depending on the different sources. So the yearly ones, which are the ones from Mystery et al., are based initially are based off metapopulations. So the researchers built up metapopulations for the different populations they were creating contact matrices for, and then model the contacts between these metapopulations for different locations. So school, work, households, and then others. And then what they did once they had these contact rates is they fitted these contact rates to the contact matrices from the Polymod survey, so this original diary-based survey, to give an overall contact matrix which is aligned with these diary-based methods. And from this, they got the yearly contact rates. So we're saying they account for how many contacts a 1-year-old has with a 1-year-old, with a 2-year-old, with 3-year-olds, and so on. And then the 5-yearly contact rates was based off Premetal. They also didn't do diary-based ones. This is also kind of synthetic contact matrices. And what they did was similar to Mystery, but kind of backwards. So they took the Polymod matrices and extrapolated from those what the contact rates would be in different locations. So again, the schools, the workplaces and households, and then other. And then they projected those into the different populations of the countries that they had. But they only looked at 5-yearly, potentially just due to data constraints, possibly.
Thank you very much, Elizabeth. Another round of applause for our speaker.